Good morning, everyone. My name is Tianying, and today I'll be talking about my project on Nano Bionic swimming, robotics, and applications in environmental engineering, which will be illustrated from the following 5 perspectives as shown in the slide, including the introduction, theory and method, results, discussion, as well as the conclusion. So as macroscopic swimmers survive in nature, they have evolved unique structures and swimming patterns under the water, which has special advantages. And the movement of bacteria at low Reynolds number environment has aroused extensive research interest. So on this basis, we are inspired to design a bionic robot on a macro scale, an artificial structure imitating the external shape, movement principle, and behavior mode of organisms in the nature. So the project aims to simulate its motion at low Reynolds number fluids and explore complex future applications in different fields. So here we first introduce the definition of Reynolds number, a similarity criterion constant in fluid mechanics to characterize the influence of viscosity. So which is defined as the ratio of the internal forces to the viscous forces as shown in the slide. So as examples shown in the slide, people, fish, and microbes swim in the water. The physical behavior and the Reynolds number of various creatures are also different because of the huge differences in the line scales. So when the Reynolds number is extremely low, the viscous force is dominant, which means the internal force plays no role and the force is proportional to the velocity only. So we aim to find out why swimming at the macro scale is so difficult and then try to design an artificial nanobionic robot that can overcome the difficulties when they swim at a low Reynolds number. So the most significant difference in macro movement is the reversibility in time. That is, any motion is the result of the current forces exerted on them and has nothing to do with the past at low Reynolds number environment. So under this circumstance, we can even move backward by exerting reverse forces, which makes it clear what a low Reynolds number implies. So scallops, for example, swim by the shock of slowly opening their shells in the water and then quickly closing them together. Since they have been doing reciprocating motions and the shells open and close symmetrically in time, so they cannot swim at low Reynolds number environment. Only if microbes break time reversibility can they swim at a low Reynolds number environment. This is what we call scallop theorem. And then, however, 2 methods are found to be efficient in overcoming the problem of swimming in the microbial world as shown in this slide, where we mainly focus on the second one, the corkscrew. So the corkscrew means that rotating their helix flagella filaments and helix cell bodies. For example, the most common E. coli rotates its flagella like a screw to meet its swimming aids, which was used as a nanobionic swimming robot model to analyze each characteristic value of the artificial nanobionic robot by programming in the following sections in this project. And then the whole programming process was based on the equations presented in this slide. We say the matrices come in since everything is linear at low Reynolds number environment. We also develop a mathematical explanation of the bacterial swimming speed with viscosity in linear polymer solutions. And then I'm gonna talk about my results from this following two perspectives. The programming part was done by MATLAB, and also the modeling part was done by Pro Engineering. So based on the known conditions, we can plot the relationship between the velocity and the pitch angle. The profile is shown in the slide. So the profile indicates that when the pitch angle changes from 0 to 45 degrees, the velocity increases with the increase of the pitch angle. However, when the pitch angle changes from 45 degrees to 90 degrees, the velocity shows a contrast pattern, decreasing with the increase of the pitch angle. And also the velocity reaches the maximum value at 45 degrees as shown in the figure. And then we still use MATLAB to simulate the two-dimensional swimming processes of an E. coli, which swims following a run and tumble process, knowing that the run speed of E. coli is 25 millimeters per second. The average runtime is 1 second and follows an exponential distribution. And also the average tumble time is 0.1 second. So using two random arrays for the run and tumble process, we can plot the profile of the speed versus time as well as Vy versus Vx. On this basis, we finally plotted the two-dimensional swimming trajectory. Then one of the random results is presented in this slide. And also, based on the plot of Y versus X programmed by the MATLAB, we could finally simulate the swimming trajectory as shown in this video. I'll just show you guys. However, the flagella on its cell body and it's should be flexible, but the software, the Pro Engineering cannot manage as vividly as the real thing. And also, as you can see, the cell body rotates in the opposite direction to the flagellum, but the difference in speed should be pretty huge, which cannot be shown obviously in the video either. And also from what has been discussed above, we are inspired to apply Nano Bionic robots into wastewater control management engineering, which do not need to have extremely complicated structures, but need to have the ability to receive radio wave signals. They can still move around as well as monitor contaminants in poor condition fluids without creating additional pollution by self-propelling, just like the microscopic swimmers in the nature. So by conveying the information they detect to the nearest robot through radio waves, the detection information will be transmitted to the central control system in the end. So in this way, the bionic robots only act as a medium for the information transmission so that we can collect and analyze the data directly instead of conventional, complex, time-consuming laboratory tests. So in addition to obtaining inspiration from the physical properties and propulsion of the creator, it is also necessary to emphasize self-perception, self-control, and other performance characteristics. Positioning in the water and environment perception. For example, much closer to the macro creatures in the nature. So from what has been presented above, the conclusions are listed below, as you can see in the slide. So in the 21st century, research in nanotechnology, biology, and environmental energy should be developed in conjunction with social development. Therefore, we may get a deeper understanding of the integrated system and put forward more innovative ideas so as to always have a hope for artificial nanobionic robotics revolution in the future. That's pretty much wraps it up. Any questions?